Okay, so last part and completely different business, the business of light emission and lasers. So first of all, what is this business with light? As you might well know already, light is a wave, but you can also regard it as a particle with photon. As a wave, you should consider the propagation in space as a combination of two mutably perpendicular fields. One of them is the electric field, and in perpendicular to the electric field, you're going to have the magnetic oscillation. That's why it's an electromagnetic wave. And the direction of propagation of the wave is perpendicular to both of these fields. So you have electric magnetic, and the propagation of the wave is the third point of the vector. So in general terms, you could consider this as a 3D vector because it's propagation, electric, magnetic. But when you actually figure out the intensity of this thing, then you can just use it as a scalar wave that goes in one direction. Now, the light that we see every day is the light from the sun. So it's the complete spectrum of the actual visible light radiation. And it's an average of wavelength, but also an average of oscillating fields. So you might see the direction, but the fields will go in every part. So when you have this thing of the electric and magnetic field oscillating in every single possible plane, then your light is not polarized. So you call it unpolarized. But when you filter off the wavelength so that it oscillates and vibrates in a single plane, so you have magnetic, electric, and the propagation, then the light is linearly polarized. Now, this can be an interesting feature if you actually want to use filters and figure out, single out a very specific type of light, and it can be necessarily for certain applications. Now, usually, when we think about radiation, we have the radiation from the sun, but also the radiation from the sun in itself is the radiation of a hot object. And this is something that we also are used to see when we put like coal on like a nice barbecue, or if you've ever seen one of the very old light bulb, which are incandescent light bulb. This comes from the fact that a hot object will emit radiation, usually in a very specific color. Why would they do that? Because you have a series of allowed energy levels, as we were discussing, above the occupied energy levels. If you use the thermal energy that you give to a hot body to start to promote electrons, you get this series of continuous processes in which you heat it up, you cool it down, you heat it up, you emit, you heat up, you emit, you heat up, you emit. So you have a series of emissions, usually in a very specific wavelength. And depending on the absorption conditions, you end up in absorption spectra or emission spectra if you actually want to measure it. Now, at a given temperature, you usually reach this equilibrium. So absorption, emission, your object is glowing, usually. But you see it at a wavelength that shifts with the temperature. This is what is called the Wien laws in like hot body physics. And there is this thing of like the black body radiation will have a peak wavelength that shifts as the temperature gets higher and higher and higher. That's the reason why when you look at stars, you have the blue stars and stars that are yellow-orange as our sun, and these two things have two completely different temperature at the surface. So given the continuous level, you kind of get the broad band of emission. You cannot expect this to stay on a single wavelength. You will get all the wavelengths involved into this business. That's why it's like a black body radiation. But the emission will peak at a certain wavelength, so depending on the temperature of the object, the wavelength goes lower, right? But on average, this thing doesn't happen through all of the electrons of the whole solid, right? So you need to do this in a very limited fashion, and it's a continuous equilibrium process. Inherently, by the way this thing is created, by promotion, emission, promotion, emission, promotion, emission, as you excite and release, the light that you get out of this is inherently incoherent. So you cannot have a single polarized direction. This will go in any direction it possibly can, and it will. But the fact that we have this business of absorptions of electrons also makes a particular case for metals, because as we've been discussing since the beginning of the course, based on band theory, you end up having a series of available levels in your band that are directly contiguous to the occupied levels. So metals usually should be able to do this like nice heating up and glowing in a very specific way. But this is also the reason why the metals in themselves are shiny, because they will get excited by the light that hits them and just continuously bump back photons at a given temperature. They're not black, even though they should be, because in theory, if you have a possibility of conduction of electricity, your object tends to be black, but the metals tend to be shiny, but shiny in a way that makes them silvery, or in certain cases it makes them colored. Why would they be colored? You have this Sulfate effect that could be varied depending on what are the levels that are involved in your bands, because as we said, you could depict the bands as a single block with no shape, but in reality, depending on the atoms that are involved in the business, the shape could be different. So with something like silver, you have a huge series of occupied energy levels. The light reflection goes throughout the whole visible spectra. So you just reflect in white. You see it shiny, grayish, but the hue, as you turn it against the light, is white. And instead, with stuff like gold or copper, the perceived color will depend on the frequency range of the light that you reflect on, and in turn, the light that you reflect depends on the one that you absorb. So copper will have relatively few unoccupied levels excited in violet, blue, and green light. So that light is preferential for you at the surface to give you then the reflection. So since it prefers to absorb the violet, blue, and green light, the thing that you get out is something that looks orange, reddish. So the material reflects all the wavelengths, but more light is in that specific frequency. Similar stuff for stuff like metal that goes into yellow, and every time you mix these three, you get a sequence of hues of the color, so a shade that changes because of these available energy levels. Now, this thing might immediately feed into, oh, but like, since we talked about metal, then what about semiconductors? And in semiconductors, you have the band gap, and as we were discussing when we were talking about solar cells, silicon has a band gap in the infrared, but for some of the other materials, the band gap might actually fall into a specific range of visible wavelengths, so at higher energy, which is higher than the thermal energy that you give at room temperature, but it could be breached by visible light. So the photoelectron energy is proportional to the frequency of the light, following this law that many of you might be very familiar with, which means that you have a minimum frequency for bridging the gap that is correlated by this equation. So this means that you can try to figure out what should be the color of a given semiconductor based on this relationship. So if I tell you that you have a 1.43 electron volt band gap, you should be able to tell me that you have a specific wavelength of gap bridging, which is the ideal one to have the optimal bridging, that is equivalent to 867 nanometers. So 867 is too high to be invisible light, meaning that this thing comes out black, because this thing is in the infrared region, so all the visible light gets absorbed. When you move to something like cadmium sulfate, the band gap becomes larger, so you have a 2.4 electron volt band gap, which corresponds to a minimum wavelength for the bridging of 517. Now this is a visible light point, a visible light that is enough to make your material yellow, because it's absorbing green, getting out yellow light. When you go instead in something like zinc sulfate, the band gap is even higher, is 3.6 electron volt, which corresponds to 345 nanometer of radiation. Now this thing is getting off the other side of the visible light spectrum, so no visible light basically gets absorbed. You're very close to the 400 bridge, so you almost get no visible light. Anything you get is this vaguely like this vaguely yellowish hue, but the material is fundamentally white, and this is what you expect to get out of this. But now that we recorrelated color not only to absorption, because it's a problem of absorption, but to the concept of emission, we could reorganize what we have as a concept for p-n junctions into something else, because we know that you can bridge with light and you do it purposefully in a p-n junction in a photovoltaic to actually get an electrical response. And what you're doing is using the fact that you basically have your P and your N junction, your depletion zone, in which you have a recombination of the carriers, and at the two sides of the junction there is like you cannot go beyond the depletion zone, but since you're trying to equalize the Fermi level, there will be a voltage gradient that develops from the N side, which is the positive, to the N side, and this gradient is the thing that blocks any further crossover of your carriers. So at the thermal activation will continuously create something, but they will just recombinate. And the issue is that creating this thing gives you this tiny minority carrier. So at the equilibrium, the number of electrons crossing from the N to the P is balanced from the other side. If you have bias, you modify the voltage and you modify the equilibrium. So a DC bias will disturb the equilibrium. You see, if it disturbs the height of this barrier, the majority carrier will start to flow, because you disturb, if you go in forward or reverse, you can get two different regions. Now when you cross and you get an electron hole recombination, depending on what is your bridge here, you might end up with spontaneous emission of radiation. So if by imposing the voltage, the recombination gives you, instead of something that is general for every semiconductor, which is a thermal dissipation of energy, it gives you a light dissipation of energy, your junction is emitting light as it recombines. Now, this thing, ideally, it's a waste of everyone's time. So when they first figure it out with gallium arsenide that does exactly this thing, so the electron-hole recombination emits light, this was very disappointing at the very beginning when they did when they were trying to figure out p-n junctions, because it would mean that your junction is not doing its job in terms of electricity, because it's dissipating a non-insignificant amount of any current that you put in to emit light at that given imposed voltage, and a light that is always the one of the gap. But they figured out that actually, what if we don't want this thing to act as our p-n junction for other purposes? What if we want it to emit light? And this was the concept behind the light emitting diodes, also known as LEDs. And so usually the wavelength emitted depends on the band gap. Obviously, the gallium arsenide in itself, given the bridge that we saw before, it's in infrared, so it's not useful for something visible. But if you dope it with something like phosphorus, then it will start to shift the emission, and the emission will get closer to the visible range, close enough that it will start to emit red light. Now, the trick here is that, as we were discussing, anything that is above the corner of the conduction band or very much below the edge of the valence band is not the optimal position. So when you get the emission, you should get it perfectly at this bridge, which means that your light emitting diodes are very narrow emission bands based on the semiconductor components. So the wavelength that you get out is directly at that super narrow emission that is your optimal band gap and nothing else. So you can have a red, like the gallium arsenide doped with phosphorus, a green, or a blue. Now, the first LEDs were the one in the 50s and the 60s. The infrared to green thing was sort of easy to obtain. It was easy to dope in this way. The one that was particularly tricky to get was the blue one. But once you get blue and green and red, then you have a very nice LED, because it means that this thing is usable, and that's the reason why there is a whole Nobel Prize on the creation of the LEDs, in particular also the creation of the blue LED. But now that we are discussing this whole business, we find ourselves with two different types of emission. So the diodes, especially if you focus them, could act a bit more like a laser. But instead, the one that you generally have, and especially incandescent light bulbs or any other type of emission that is uncontrolled, is usually multi-wavelength. So multi-wavelength, multi-directional, and inherently incoherent. When we think about lasers instead, we're not just thinking about something with a very specific color, which the diodes can give you. You don't only want it monochromatic, you want it incredibly directional, so anything that is not away from a specific direction is not emitting light, and you want it to be coherent. So you want that trick of where are we going with this specific electromagnetic field. So this is a trick that distinguishes a general light emission from a laser thing. Now, there is a fundamental requirement for a laser, which is you need to have metastable energy states. So not only a single energy state and maybe another one where you can excite and then you go down. in energies, because that's the general case that you also have with metals, but that's not what you want in this specific case. You want multiple ones, multiple accessible one, or which some are actually metastable. And you don't only want to excite and go down, and excite and go down. What you want to achieve is a population inversion. So at the normal state, you will have most of your electrons in the ground state available at that temperature, and some of them will go up and statistically recombine down. When you get to the point of population inversion, you actually throw most of your electrons at a higher excited state, and the ground state is depleted. So if you decay from that point, then it's different. And you have a whole population that can actually collapse down, but it can only happen if you have multiple levels in between. So how does this thing look? That the normal excitation just goes one excited, one down, you emit, and you call it a day. Anything that is higher than here will relax down, thermally speaking, and then emit from the corner. If you manage to get the population inversion, then you are building up whatever is up there without decaying, until something stimulates the emission, and the moment it emits, it just causes an avalanche, so all of them will decay at the same time, and usually this emission is a first photon that gets pumped and bumped into the system. First thing just drags everything down, and at that point you don't have a simple light emitted from one recombination. You have an avalanche of photons being generated by all this population inversion collapsing back down into the ground state, naming that you have light amplification by stimulated emission of radiation, a laser. That's where it comes from. Now, what do you need to achieve a population inversion? You cannot do this with a system that has one ground state and a single accessible ground state. You need intermediate states, because otherwise it's impossible to achieve population inversion, because you will be doing something weird, and you cannot just flip the population of the states. You cannot have the ground state completely empty and the excited state completely populated. This is unphysical. Your system will never be able to actually sustain it. So what you want is actually an intermediate state that by its nature does not get occupation, and that's your empty point. So what you can have is either from a ground state to an intermediate state, and then the intermediate state has the quick collapse, which is the thing, but instead of collapsing back into the ground state, you collapse in an intermediate level. So that intermediate level is the one that is getting fed by this series of excitation. So the normal physical process of I excite and then I relax is available, but it doesn't relax down to the ground state, it relaxes down to an intermediate state. Now that intermediate state is the one that will cause you a laser emission at some point, and since it got populated, then at that point you will have a population here that is incredibly higher and will just emit radiation all at the same time, and everything will go back into the ground state. Even better, it's a 3-point level system, because this makes your life even easier, even if you have very few carriers being able to get excited to the normal excited state. Because in addition to the intermediate state in which you will collapse down anything that gets excited from the ground state, you will also have a second intermediate state. Now, achieving population inversion when you have something like A and A prime is inherently easier, because A prime is empty. So a population inversion between A and A prime is huge, because anything that is up there, it's not down there. And the lasing emission will be incredibly strong when it collapses down to this A1. And then from A1, we'll just relax back non-radiatively into the ground state. So this is what you want. You want a multi-level system with multiple energy states available, in which you can actually excite, revert the population, collapse, and the lifespan of this thing must be different in itself, because the thing that we saw in normal emission is just that the lifespan is too short, so you can never achieve population inversion. If this thing and this thing live long enough, then you can keep populating them and then emit all at the same time. Now, what system can actually work with this type of thing? Something like aluminum. So alumina is aluminium 2O3. In itself is colorless. So when you have a crystal of this thing, is a gem, it looks like a sapphire. It's very nice, but it's colorless. So in this material, you have an almost octahedral coordination of aluminum with oxygen in distorted octahedral, so they're not precisely octahedral. Now, when you dope it, you could make a nice trick, right? Because when you dope it, you replace something like aluminum, which is a main group element, with something like chromium-3. Now, aluminum-3 and chromium-3 have the same oxidation state, so your structure could like it. They are vaguely similar sizes. Your structure could like it, but if you just substitute like very little of it, so between 0.02 and 0.05% in weight, your chromium at that point will have the same oxidation state, but a series of partially filled energy levels and orbitals. Now, these ones are the type of things that you can actually use to get the excitation and the inversion, because it is these electrons that are excited and cause the absorption of a series of wavelengths. So your material, which is a chromium doped alumina, becomes a ruby. So this thing by itself is red, right? And you have a series of energy levels available that can actually strongly absorb blue light and stuff. Now, the trick of ruby is that in itself it's fluorescence, so this thing have a longer lifetime. And having a longer lifetime means that if you pump your system, so if you give it a way to get incredibly excited by a series of light, right? So anything that is in blue-green will just start exciting electrons, and you have a metastable point here that is very long-lived. It means that you start inverting the population. So these are the d electrons, and you get promoted them from the ground state into the higher state. So you're using the trick of the fact that you have a whole structure with its energy levels and the added energy levels of the dopant. There is a lot of ions that are stimulated, and then when they transition in phase with each other all at the same time. They give a single intense coherent pulse of a radiation that is red. So the laser pulse here, so you excite and then it emits. The emission is very precise, is pulsed at 250 microseconds. So, and it can be very, very strong depending usually on how much you dope. How does this look when you actually have your tiny flashlight with a laser? It looks like a series, something with a series of mirrors, because you need to be able to build up this population, and a lamp that is the thing that is pumping up your system. So this thing will start to glow up to begin with, is the thing that it starts to excite your ruby, and then the first photon of fluorescence of the ruby is the thing that causes the avalanche. When you're after a certain point, the mirror opens up and you get a pulse of radiation going out. Nice. Another system, which is a good system, is this Garnet structure. So it's another type of aluminum oxide, but this time the general material is the yttrium aluminum oxide. And given this nice structure that you get, this thing is called a garnet. So you have different type of coordinations, and when they are put in this arrangement specifically, it becomes a garnet. Now you have a neodymium type of doping, so you substitute yttrium with neodymium, you do some doping into the structure, and what you end up is with something that is called the Neodymium Yag Laser. You might have seen this this type of label somewhere, and this thing is a 4-level laser. So depending, this can be vaguely dependent on how much neodymium you're putting in, but unlike the ruby that particularly likes green and blue light to get excited, up here you can consider that you have a series of possible energy levels to get excited with, but they all come down to a very specific level that is given by your neodymium. So you can just excite, you get a nice population inversion, you populate this level, and at that point, when it starts to decay, it decays with a wavelength that is basically 1,000 something nanometers. And this thing is infrared, so you can be like, oh, is it interesting? But this thing is, it could operate impulsed with different pulses, with incredibly strong radiation, and with this transition at 1,064 nanometer is very efficient, meaning that you can have a very substantial power, either continuous or pulsed in mode of operations. So this is the type of laser that you use in surgeries. And if you ever done anything with a laser on for like procedures and stuff like that, you know that these ones on the skin can get particularly hot, and by the fact that it's in infrared radiation, it can actually penetrate deeper, whereas visible light just bumps off your skin for the most part. So this is a summary of a series of lasers available. So you can see output power, type of mode, can you pulse, continuous, what type of material are inside. And you can see that depending on the doping of the neodymium and what is your material, and is it crystal, is it glass, you can get slightly different radiation, but for the most part they tend to be in infrared. But you could get substantially different output powers, so you can actually tweak this thing to act as a simple laser in infrared, or as something that is going to burn tissues or stuff like that, or something that can be pulsed at a very specific way. And you also have this type of possible semiconducting lasers, in which case you just have to design your material in a way that emits all that light in a very specific direction. So you have also a series of applications, just to remind you why is this thing useful. Now, this concludes our 5th lecture. This is your series of learning objectives, and we are going to discuss this whole thing when we have our live session, but make sure to have some questions, and if you are afraid that you will forget them, you can put them in the Canvas page. See you soon!